Hi, I'm Katrina, and today I'll be discussing a biomechanical analysis I performed using OpenSim. Recent developments in muscle imaging are allowing us to see as never before in vivo sarcomere lengths. Of the many uses of this knowledge, this project addresses using it to improve patient-specific treatments of neuromuscular and musculoskeletal disorders. Many patients with cerebral palsy suffer from contracture, a condition in which muscles are abnormally short. As a result, the corresponding tendons are stretched more than usual to span the same distance between attachment and insertion. This passive force, in turn, stretches the attached muscle fibers, and this passive force causes extreme plantar flexion and likely the tiptoe walking observed in many cerebral palsy patients. This condition is referred to as equinus. With regards to the calf muscles, there are two distinct contracture scenarios, one in which only the gastrocnemius is shortened, and the other in which both the gastrocnemius and the soleus are shortened. Optimal tendon transfer surgical procedures, which ideally restore range of motion without excessively weakening the muscles, differ between these two scenarios. But the optimal tendon transfer strategy also varies by degree of contracture. As we are on the verge of being able to directly quantify contracture, we should look toward incorporating this knowledge into existing biomechanical simulations. As a preliminary study leading toward this goal, I chose to investigate the sensitivity of normal gait to shortened muscles. I was interested in the following. How do different degrees and types of equinus affect the ability to track normal walking kinematics? What are the resulting activation strategies? And what muscle forces and reserve actuator exertions change with progressive amounts of contracture? I used the Gait 2392 OpenSim model and Chan-John walking data, as well as a procedure adapted from How Robust is Human Gait to Muscle Weakness. I iteratively shortened the appropriate optimal muscle fibers without changing their corresponding tendon slack lengths, and reran computed muscle control to see how these models with progressively more shortened muscles might still enable the same normal walking kinematics. The OpenSim simulation results confirmed that as contracture increases, the tendons and their corresponding muscle fibers experience increasing amounts of passive force. Even when the soleus is not shortened, it still experiences higher passive forces when the gastrocnemius muscles are shortened. This makes sense given the complex and intertwined geometry of the triceps sura muscles and their associated tendons. One of the most notable changes in activation strategy was a sharp increase in the tibialis anterior muscle. This dorsiflexor was called into action in order to oppose the extreme passive forces in the contracted plantar flexors. Perhaps, for patients with only mild amounts of contracture, strengthening the tibialis anterior muscle would enable more comfortable gait. Eventually, the tibialis anterior compensation is not enough to account for the extreme passive forces in the calf muscles. At this point, the computed muscle control tool must utilize the ankle reserves to still track the desired motion. Increasing use of these reserves indicates that a patient with the corresponding amount of contracture is increasingly unlikely to be able to walk with this normal gait. Total maximum ankle moment needed for normal gait is about 40 Newton meters, and reserves greater than 5% of total moment are conventionally indicators of failure to track. On the left, we see that reserves are definitively too large, between 20 and 30% of contracture. On the left, we see that significant reserves are needed between the 10 and 20% contracture cases. It is difficult to exactly define what successful and unsuccessful tracking is, especially because the normal case of this study required reserves technically defined as too high. However, we can take away from this study that both types of contracture lead to difficulty in early stance phase dorsiflexion, which has been observed clinically, and also that combined contracture in particular probably causes the subject to, quote, heel strike onto a plantar flexed foot, leading to tiptoe walking. Based on this simulation, we could clinically test the hypothesis that patients with equinus who tiptoe walk most likely have combined contracture. Using this data, I did an example tendon transfer surgery. As recommended by prior literature, the optimal strategy for a case in which both muscles exhibit 45% contracture was differential lengthening of the gastrocnemius aponeurosis, gastrocnemius specific tendon, and the Achilles tendon, calf muscle tendon as a whole. As expected, the tendon transfer resulted in dramatically decreased passive forces, but further study would be needed in order to ensure that the surgical strategy minimizes muscle weakening, as well as maximizing range of motion through the reduction of these passive forces. Additionally, further study may involve building an optimizer in OpenSim that finds the optimal tendon transfer procedure for a given set of patient-specific calf muscle contracture measurements. It could be particularly important to include these measurements in biomechanical simulation if a patient exhibits asymmetrical contracture, in which case the surgical strategy would be both patient and limb specific. Here we've looked at generalized reserve forces needed to make a model with progressively shorter muscles complete normal walking kinematics, and we've seen how compensatory activation strategies evolve, as well as how forces change within the system with progressive amounts of contracture. Future work may include confirming that equinus most often results from combined soleus and gastrocnemius contracture, including other muscles exhibiting contracture in the model, finding optimal surgery strategies for different types and degrees of equinus, and simulating different tendon transfer surgery strategies for patient-specific measured contracture cases. This sensitivity analysis could be performed on other parameters as well. Thank you very much to Daniel Jacobs, Tom Uchida, Matt Demers, Scott Delp, the OpenSim team, and Nimble Lab for their help with this work.